Hi everyone, welcome back and welcome to the Enigma stage. We're going to have a great session coming up now where we're going to have some lively demonstrations from some leading researchers. We've got a mix of different demonstrations today, and there's going to be an opportunity to ask questions to each research project after they've shown their demo. So please put your questions over in Slido. I find that there's sometimes a little bit of a delay with the Slido, so if you have a question, please either try and type it as quickly as possible or put it in Slido while the presentation is going on. Tends to be that once we start the Q&A, if you put it in there, it might be a little bit late by the time we get to it, but we'll try our best. So make sure if you have a question, type it nice and early. Okay, without further ado, let's go on to our first presentation. We have Trevor Martin, who's Professor of AI from the University of Bristol, and joining him is Leah Claireaux, big data analytics researcher from BT. And they're going to be presenting Intelligent Log Parser, a long-term collaboration that's been happening between the Bristol Intelligent Systems Lab and BT's Future Security Research Group. Leah, Trevor, over to you.
Hiya, I'm Leah and I am BT security researcher, and I'm working alongside Trevor to downstream ILP to production security data to pass as many records as we can from logs that currently cannot be passed, because inevitably more records means more data and better analytics.
Thank you, Leah. As Gemma said, I'm Professor of AI at University of Bristol. I'm also a BT Senior Research Fellow, which means I spend about 60% of my time working with the Future Cyber Defence Research Team at BT. And this demo is one of the results of that collaboration. So if we can go to the video. Artificial intelligence is being used more and more widely to help detect and respond to the ever-increasing threat of cyber attacks. Intruders and malicious agents are constantly evolving new techniques to carry out attacks. For defence to be effective, data from a wide range of sources must be collected at rates exceeding millions of events per second. Machine learning has the potential to understand patterns in network telemetry, but it's no good unless it's built on reliable and representative data.
This demonstration focuses on the first step in that chain of processing, intelligently gathering the raw data from logs and other monitoring tools. Data from a variety of sources must be integrated and standardized so that subsequent processing by intelligent software and human analysts can go ahead.
Traditionally, this data extraction uses handcrafted regular expressions to identify and parse the records. As well as being time-consuming and fiddly, this is not a very robust approach because regular expressions need a precise match. Quite frequently, software upgrades or configuration changes can lead to records that no longer match and must be diverted for reprocessing, or in many cases, simply discarded. Here, the pattern is expecting an old-style IP address and rejects the record, even though a human might accept it as a close match to the pattern. Obviously, losing data at the start of the monitoring chain can have some serious consequences for later processing, and the Intelligent Log Parser has been developed to assist in this process and counter the potential loss or misclassification of data in 4 ways. First, it allows approximate or fuzzy matching to be used so that close but not exact matches are allowed. Second, it monitors the approximate matches and suggests alterations to the existing library of regular expression patterns. Third, it can identify new record types and suggest appropriate patterns to extract data from these records. And finally, it can analyze the regular expression library to help analysts develop a better version. In this demo, we take a brief look at 3 of these areas.
First, we can use the Saturn visualization software to get an overview. Here, we look at the most recent 10,000 records that have been processed, and we can see on the right of the screen that most of them have matched known patterns of regular expressions. And on the left, we can see how they group together. There is a significant proportion of records that haven't matched regular expression patterns, and it is interesting to drill down to see what is happening. We can see 2 groups of records that don't show an exact match with any of our patterns. We'll look at this one first, as it is mixed up with some records that do match a known pattern. Focusing on this region shows that it is a mixture of records recognised as window log entries and some non-matching records.
If we examine them with a slightly different clustering view, based on the approximate match distance between records and the known patterns, we see that our non-matching records lie almost at the centre of the records that match the known pattern. That tells us there's only a small mismatch, and by looking at the cluster properties, we can see that the closest matching pattern type is the Windows log. We can look at a few records that match the Windows log pattern, and some that are close but don't match exactly. We could try to find the difference between the groups of records by inspection, but it's easier and more reliable to adopt an alternative view of the data where these differences become more apparent. We can view the records in their entirety and look at the patterns as graphs. The blue graph and the blue row show the pattern of the non-matching records, and the bluish records at the bottom of the table are examples where there isn't an exact match. The red graph and the top row show the pattern, and the reddish records further down are examples of exact matches to that pattern. Looking at the graphs highlights the non-matching fields and also tells us how much we would need to generalise the existing pattern to make it match all of this data without overgeneralising. For this column, we would need to replace the regular expression for word with a more general regular expression. The key to this generalisation process is a lattice formed by analysing the regular expression library. The direct link here indicates that every string accepted by the regular expression for word is also accepted by syslog host. We can get an idea how this lattice is constructed by looking at regular expressions for dates, where European and US formatted dates accept some common strings and some unique strings. This allows us to define a general date class that will accept both. We also allow an approximate version of generalization, but won't go into that today.
We can use the graph and example-based view to look at different patterns that are defined for a particular log type. Here we have 4 patterns for the Windows log, and this can help analysts find redundancies and gaps in the coverage of the patterns. A small sample of matching records is also shown, helping the analyst to see variations in the patterns.
Returning to Saturn, which is a visualization analytics package developed at BT, we can see there's a second cluster of non-matching records. In contrast to the previous case, there are no nearby named clusters, so it looks like these records are an unknown log type. We can take a look at examples of the records from different groupings, and we can see that the data is quite similar in both cases, possibly differing as we look at some of the fields. We can also look at the specific patterns derived from each group of records, and the next step would be to combine these patterns using the generalization hierarchy and automatically add the patterns to our library, or present them to an analyst for examination and approval.
In summary, the Intelligent Log Parser tackles the problem of brittle regular expression parsers that are easily broken by small changes in record formats. It can generalize existing patterns where there is a close match or generate new patterns, and also gives an insight into the coverage of the regular expression library, which is not an easy task for humans. Overall, it gives us a much more complete set of data for subsequent processing, and forms the foundation for reliable machine learning applications later on in the processing chain. The software is currently undergoing trials and will be deployed as a key component in the data ingest pipeline of BT's security analytics platform.
Thank you very much for that, Trevor and Leah. Are you ready to go for questions, or is there anything else you want to add before we go into that?
No, I think we're good to go with any questions.
Great, awesome. So As I said earlier, everyone who's watching, if you could get your questions up in the Slido. Though I haven't seen any come through yet, so I will ask a few of my own first, but make sure you get typing now so that we've got a bit of time to ask of Trevor and Leah. So to Trevor and Leah, I think that the first question I'm always keen to ask, and I've asked this of most of the researchers who have spoke to over the last day and a bit, is what's the sort of next steps for this project? What are you hoping to kind of, I guess, move forward with? What's the next thing for the collaboration for the research?
Well, I think on this particular project, Leah is probably best placed to tell us about BT's plans for this.
Yeah, so we're looking to actually try different logs and see kind of if there's a particular log that can't be passed increasingly amount. So take, for example, operating system logs are more difficult to pass than others, and we may have a higher percentage that can't be passed through the system. So we're looking at getting some results out from the ILP Parser to see how many can actually be passed that previously couldn't.
Amazing. And we've had the first question, we've had two questions already come through on Slido, so let's go to the first one here. This is from Carolyn. She says, thanks, exclamation mark. No worries, Carolyn. Have any surprising challenges come up during trials?
Well, I think probably the first challenge is actually moving from a kind of proof of concept research level tool to something which can be used in real life almost. And I do think it's very easy to underestimate the challenges of making that transition. Leah, have you got anything that you would like to add?
Yeah, so we've had to kind of get to grips with the existing parsing methods for the data. So obviously we've been working on this project outside of understanding the infrastructure. So going in and seeing what lays there at the moment and how we can actually kind of intertwine this new parser with existing methods. I think kind of seeing how we can actually add additional purposes to that has been a big challenge.
Amazing. Next question we've got here from James. It's got 7 upvotes, so I guess a lot of people in the audience are keen to know the answer. Have you looked at alternative approaches to extracting useful content from logs, perhaps using NLP techniques?
Yes, I guess one of the features of the logs is that they are semi-structured or verging onto structured, because people put things in very rigid formats. I guess sometimes there is a little bit of capacity for using NLP techniques, but what we're trying to do is pull out the key fields. So dates, times, IP addresses are the obvious ones, and to be honest, regular expressions are where pretty much everything is focused, because they're very fast. If you start introducing natural language techniques, you need a lot more processing power, and you slow things down. We are looking at very high transaction rates here. Leah, anything you would like to throw in there?
No, just that it's kind of at the very early stages of looking at new ways to parse these unknown logs. So kind of new techniques alongside the parser are definitely going to look at being explored as well. So I think natural language processing, we've got a couple of projects looking at that currently in research. So if we could perhaps take some of those techniques and apply it to this as well, to gain even more benefit, faster processing, that's something we would look into.
Let's see if we can squeeze 1 or 2 more questions in while we've got them. So we've got another one that's got quite a few votes here. How do you determine the distance between regexps during clustering?
Okay, I think that's probably mine to answer. We've got 2 approaches. It's essentially based on that lattice structure, which looks for kind of common strings that would be accepted by 2 or more regular expressions, and if you've got a direct link in the lattice, then one accepts everything that another accepts. If they have common parents, then there's a kind of proportional common set of strings that they accept. We can either measure the similarity using a kind of empirical approach. So we just throw in a whole load of strings at the regular expressions and see what they accept and what they don't. Or we've actually developed an analytical approach to it, where we can look at the structure of the individual regular expressions and figure out how much overlap there is. Obviously, if you try to do that in general, it becomes very difficult. But because we're kind of restricted in the alphabets and the lengths of the strings that we're looking at, we can actually do that very, very quickly. And once you've done it, you've got the similarities.
I'm going to ask you one final very quick question, because I think it's going to be a bit of a yes or no one. Is Saturn available outside BT?
Leah?
Yes, I believe so. Yeah, there's it's currently within our kind of research demonstration showcase, so it can be applied to clustering all different types of data sets, not just around security.
Amazing. Thank you so much, both Leah and Trevor, for taking us through this and answering all the questions. There was loads of questions through in Slido, so I'm sorry to everyone that I didn't get to your questions. I'm sure Trevor and Leah would welcome any questions direct if you have them later on down the line. They're nodding. Good stuff. Okay, let's move on to our next presentation today. Next up is Miroslaw Bober, Professor of Video Processing at the University of Surrey, and he's going to be talking about creating machines that can see and hear. Miroslaw, welcome to the stage. It is all yours.
Hello, good morning. A pleasure to be here. So today I'm going to talk about how we can create machines that can see and hear in order to understand the world around them. Yes, so we have our brain was really created and developed over 500 million years to help us to survive. So that's quite a lot of time, 500 million years, to actually not only master the hardware side of it, which are the neurons, but also the software. The software talks about or is about analyzing the information. And when you think about the complexity of information we as humans are faced today, it's huge. It can be anything. It can be complex chemicals, it can be environments, it can be mathematical formulas. And we actually are quite good in interpreting that information. So how about the machines? I mean, are machines as good as we are? Well, they are pretty good. So you have an example here. We have an image, and we can understand that there is a horse and a person, and this man is feeding the horse. So actually, we can interpret images, but this is really not a true perception. We would like to be able to build the models. We would like to learn. We would like to make the next step. We would like to find out how to land on Mars from the information that that is around. So it's really like this child. I mean, this child just learns, just plays with things around it. And it learns how to generalize, how to discover, how to create. So this child is really learning to learn. So how can we build algorithms that are actually ready to learn? They learn to learn. So I would like to tell you about our algorithms and what we've done in that domain. The problem at hand is the recognition of any object, location, product, things that we have never seen before. And if you think about a deep network here, a convolutional neural network, it's a typical design. It would take an input image, it would apply a number of convolutional filters. This filter looks for features that are meaningful. For example, eyes can indicate the presence of face. And at some point, this network will apply max pooling. It will just take the strongest of these features and will then use that to interpret what is seen in that image. But actually, taking a max operation or even average operation is not really ideal, because it's a bit like the first thing that comes to your mind. When you want to take decision, when you want to learn about things, you actually have to consider everything that comes to your mind. You have to prioritize. So how can we actually do that in an algorithm? So we developed this algorithm called Remap, where we actually measure the amount of information for a given task within the net. And that's measured using entropy, and it's measured on the fly, and that's used to balance the information. So that was a new idea, and we thought, well, let's try how that works. So we joined a worldwide competition organized by Google on Kaggle, and that competition was about recognition of locations and places using actually one of the largest, probably the largest data set of 5 million images with 200,000 landmarks. And we joined this competition to test our algorithms against some very strong competition, including teams from Naver, Facebook. Baidu was actually running half of the computers in China on that competition during that time, as we've learned later. And we were actually very happy that our Remap algorithm won that competition. So that was really a proof that measuring information and actually learning to learn is a good strategy. So as a next step, we've developed a new architecture called ACTNet, where we apply parametric functions that you can see here on the right to actually learn to amplify or select activations that are important. So it's a bit like this child that is learning that maybe a red block is actually a big one. So it's actually very useful to start constructing something with and then build on top of that. And below here, you can see the KL divergence. The KL divergence is one way to measure information content. And on the left, you can see direct aggregation, where we only have just classical way of max pooling or sum pooling 1.15. And with the aggregation proposed here, we can actually more than double the amount of information. So in practical terms, what it means is that on the left here, we have example of a query. So here is some location in mountains. And when we run the algorithms, we can find that the ACTNet actually can find the same location. So it's the same mountain at a different weather condition, different zoom, different lighting, completely different foreground objects. It can still locate precisely the actual location. And the same obviously applied to building and other objects. So we've taken this algorithm. It's not really only about the object recognition location. It can be extended to any area and used in an area. So we've worked with the NHS to actually look how that would perform in terms of AI diabetic retinopathy detection. And the idea here is we will not only indicate which patient needs treatment or perhaps examination, but because of selection of the information, we can also help to highlight why the decision was taken. So the algorithm doesn't only tell the doctor, look, you know, that there is a retinopathy here, I think you should examine this patient. It actually tells precisely why. It indicates, as you can see on the screen, it indicates the local areas that are indicative of the disease. And you can actually see here that what the algorithm detects is actually very much aligned with what the clinician think is the indication of the disease. Another area where we use this concept is semantic labeling of videos. So here the task is to understand what the video is about. Semantically, why the video was created. This is not a very simple task because actually what you see in the video, the objects, may not necessarily indicate what the video is about. And this algorithm is using audio and video information. It's aggregating this information. And again, we took part in a competition on semantic labeling of videos, and we received gold medal for that algorithm. So I'm going to show the algorithm in action. It's been actually trained on 50 years of videos, okay? So this algorithm has seen 50 years of YouTube videos, which is more than anybody here, I think, in this audience could ever dream to see in their lifetime. So let's have a look. What you will see here is the videos displayed from some database at random, and on the right, you will actually see the interpretation of the video. So the semantic interpretation, this is done immediately. So it's actually much faster. You don't see the video yet when the algorithm already knows what the video is about. But here the algorithm thinks that this video is about hair, and it's about fashion, and it's about hairstyle. And actually it's correct. It is video that shows and demonstrates different hairstyle and how you can let's have a look at some other examples. The algorithm knows about 5,000 terms. So in this particular case, the algorithm says, yes, well, this is about piano, it's about the pianist, it's about the musical keyboard, which is probably not so difficult. Here, yes, somebody is talking about their smartphone gadget and a telephone. Let's see a couple of more examples. So here the video is about FIFA 15, sports game and football game. But actually, it is a very rich set of semantics that the algorithm can address, including complex things like, for example, it would look at the video presenting the modification to the car, and it would actually understand that the video is about the modification to the engine in a car. I think I'm running out of time, so let me just go to conclude. So what is the take-home message? It is really a very simple message. We have to give the space to our algorithm to learn how to learn. And of course, there are many ways to achieve that, but this ability to actually improve your knowledge and improve the model that you can build is very, very important. So thank you very much from all us at Surrey and the CVSSP group, and I'm happy to take questions.
Thank you very much, Mirek. We do indeed have quite a few questions that have been submitted to the Slido, so thank you everyone for engaging so far. Let's go straight to those. So the first one, with quite a few votes from Caroline, says, thanks, Mirek. Can you give some intuition as to how entropy is used in the learning process and why this performs better?
Okay, so the entropy basically helps you to distinguish. So for example, if you have a decision process between A and B, then you look at the distribution or the distances of certain features that may indicate A or B, and you look how separated, how this feature helps you to separate the two distributions. And the more separated they are, that means that this feature is actually more powerful in the decision. So that's the way it works, and that's one of the way to measure information. So please have a look at our papers. I think that's all we have the time now, but it's one of the ways to actually measure how certain features or locations in the image at certain layers indicate or help your decision.
Awesome. Thank you, Mirek. Let's go on to the next one from Julio. On retinopathy screening, would you give an intuition of how different the approach is compared to DeepMind's on retina diseases, e.g. is it a different architecture?
Yes, it is very different architecture. So the DeepMind architecture does not actually explicitly look at indication of the disease. So it basically trains the nets and says, okay, this is disease, this is not disease. Our architecture uses the information content to explicitly indicate the regions that contribute to this decision. Again, please have a look in our publications.
Awesome, thank you. Next one is from Colin. Really interesting. Could your approach use a human in the loop to inform importance in the features?
It's an excellent question. Absolutely. And so you can measure this information, automatically using some mathematical tools, but actually you can have a human in the loop, and that's the direction we are going into, where you actually use our creativity and actually feel the seventh sense. Sometimes we feel this is a good direction to go. And if you can feed it into algorithm and share your knowledge, that's probably producing the best results.
Next one on the list is from Andrew. Very interesting. At the beginning, you mentioned machine hearing as well. How can this approach be applied to things like environmental sound recognition?
Absolutely can be applied to that. So if you think about the audio analysis, the usual way to approach it is to create an image which is the frequency-based representation. So it's actually then progressing as an image processing problem. And again, there are frequencies. There are audio features that are more informative than others. So if you can pick this out during your processing, it can improve the performance. And in fact, we use this algorithm to recognize birds. There was a paper about that, and it gave significant improvement.
Awesome, love that. Next question, sorry, the questions keep moving around, so I'm just trying to keep track of which one we haven't asked. Okay, next one. How important you think is working on more efficient algorithms for semantic understanding of videos and images, for instance, trained on less data using less compute?
Well, it is very important, and it's a very good question. So obviously there is a trade-off between the volume of data, and if we can train with less data, that's great, because quite often we don't have the data, or we don't have the compute capabilities. So in this particular case, we had a lot of data, and we had the capabilities to do it. But actually, by measuring the information content, you can train better with less data, because your training task is more informed, and also the algorithm can pick up the real important features that deliver, that support your decision. So it does help actually in reducing the training size.
Amazing. Next one we have here from Sam. Most of the demonstration videos with the semantic labeler included relatively static images. Does it struggle with more dynamic visuals?
No, I don't think it did. That was a very short presentation. So it is actually, this particular algorithm is not using optical flow, or it doesn't use the dynamics. It should, and it would be better. It simply because of the volume of the data, it is using a kind of fingerprint. It's actually an average fingerprint across video, and it works pretty well. Using dynamic information would definitely help, would make probably the algorithm more complex. So, but we didn't find that the dynamics impacted the decision negatively.
Okay, amazing. I think we'll go with probably just one more question for now, so that we can make sure we've got enough time for all our presentations. So let's go with the next one, which is from Rebecca. What future applications would you like to apply your system to? It seems that your system has fascinating NLU applications through its use of grounding.
Yes, we just respond to the interest from industry, and we build the capability. So we want to move farther with hybrid nets, the nets that would interact with humans and could, use and learn how we actually learn. So it's a very fascinating area. I think it's just starting. And if you think about this child, this child will keep on learning to learn through the entire life. So that's exactly what we would like the algorithms to be able to do.
Awesome. Thank you so much, Mirek, for your presentation, for answering all these questions. Again, there's still some coming through on the Slido, so people are obviously very interested. Again, I'm assuming it's okay for people to just be able to contact you directly if they want to talk more about your research. Absolutely. And thank you for listening. Awesome, great. So we're going to have our next speaker up. We're going to have to shimmy the slides around a bit, so there's going to be a little pause between this introduction and them speaking, but do hang on, we are still here. We'll just be putting a little holding slide while we get set up. So next up, we've got Kacper Sokol, a senior research associate at the University of Bristol. Kacper will be giving a demonstration called "Did You Get That? The Intelligibility of the State-of-the-Art Explanations in Artificial Intelligence."
Hi everybody, I'm Kacper, and in this demonstration I will show you how machine learning interpretability can go wrong, especially when the explanations look appealing. So let's dive in. We'll start with images, since these explanations are quite intuitive for humans. So assume that you have a black box model and you have an image of a dog with a tennis ball, and you predict this image, and this is what you get on the left-hand side. So more than 99% tennis ball, and the remaining 1% split between golden retriever and Labrador retriever dogs. So you may be interested why the dog receives so little probability, since it's so prominent in the picture. And to do that, we use explainability. So let's have a look at an explanation of a tennis ball. So what we do here is we split the image into regions, and then we try to assess how important each region is for this prediction. Does it influence the prediction in a positive way or in a negative way? And this is the explanation you can see on the left-hand side, which is also visible on top of the image. So in case of the tennis ball, what happens is that the region number 13, which is the tennis ball itself, you can see it singled out here, has positive influence, followed by region number 11, which is to the right of the ball, and then with some negative influence from the background here, and again positive influence here, which kind of makes sense because since we're predicting a tennis ball, the tennis ball takes the top score here. But what about the dog? So for an explanation of a golden retriever, we use again the same segmentation, but the explanation is quite different. So here, as we could have expected, the ball and the adjacent segments, so 13 and 11, have negative influence, with then some positive influence from the background here and negative influence from the background there, which is not really very intuitive. I can't really tell you why the model thinks that the background is important here. So what we can do, we can actually jump straight into the explainer, and how the explanations are produced is with a surrogate explainer. So I'll give you a brief description, which is for tabular data. We have a complex decision surface, which is the pink region you can see there, and then a single instance, a single data point that we are trying to explain. And in order to do that, we approximate this complex decision boundary with a simple model, in this case, a linear model, that can help us to generate the explanations. This happens in 3 stages, and these are interpretable representation generation, data augmentation, and explanation generation. This may not tell you much. So for images, this is image segmentation, which we have already seen, segment occlusion, which I will show you on the next slide, and then assessing segment importance, which is the actual explanation. So let's play with an explainer. What happens in order to generate these explanations? You create a random set of images with different regions occluded, and you can see these random images to the right. You occlude parts of the image in order to remove it before passing it onto the black box to see whether removing this information affects the prediction. And then if it affects the prediction significantly, you can then reason that it is very important for this particular prediction. But there are 2 very important parameters that you can choose here. And the first one is the occlusion color, since you can't really remove part of the image before assessing its importance. You have to use a proxy. In this case, you just occlude it with some black patch in this case. But you can also change the color. So let's see what happens when we use different occlusion strategies. So if we use white occlusion, for example, you will notice that first of all, the regions that the explainer picks as important are different, and also the magnitude is different. And this applies to all sorts of various colors, as you can see. Here is a random coloring. So there's not really a very good answer here. What you can also change is the granularity of your segmentation. So for example, if I decide to create more segments, the explanation will also change, and the segment may change as well. And this happens for other colors. But the interesting thing here is the mean occlusion strategy. So what it does is it hides away a piece of image by replacing it with the mean color of that particular segment. So you calculate the average color of that segment, and this is how you remove it in order to assess its importance. But what you'll notice is that this image is still very recognizable, especially, for example, with the ball. And what is more, as you increase the granularity, so the number of your segments, this becomes more of a mosaic. And I guess many of you would still be able to tell that this is an image of a dog with a ball, even if I occlude all of these segments using mean occlusion strategy, which tells us something about it as an explainability mechanism. Because if we can, as humans, can still tell after occluding the image that it's a dog, I don't think a black box would have that problem either. Right, let's move on to another example. And this will be tabular data. In this case, I will use the iris dataset, which tries to classify iris flowers into versicolor, setosa, and virginica based on 4 measurements. So these are petal and sepal width and length. Let's start with a global explainability mechanism. So in this case, I plotted both of these measurements here in order for you to see that. And the colored dots represent different classes. Just by visually inspecting the data in this case, you can clearly tell that petal length and width should be important, because using them, we can separate the colored blobs. And you can see that reflected in our feature importance metric. Even with as simple methods as this one, there can be parameters, which in this case is the metric that underlies our importance scores. So we can change the metric, which affects the explanation itself. In this case, this is only the magnitude of the explanation, but you can imagine that in more complex cases, different metrics can give you quite disparate feature importances. Right, let's come back to our surrogate explainers. So in this case, the 3 steps required for us to generate the explanations are feature partition, location randomization, and partition importance. So let me show you these on an example. So in order to create something meaningful for humans as an explanation, we need to partition each features. Here I chose the 2 important features that we identified a few slides back. And then the explanation is again importance of this partition. So here we are explaining the yellow star, which is in the red blob. So we are explaining an instance of setosa, and we want an explanation for the class setosa. So now I have a question for you. Given that we can change the partition of the features, what do you think would happen if I move this line, so petal length split at 4, a bit to the right? I'll give you a moment to think about it while I move the parameters around. Right, so the explanation didn't change, and there is a very good reason for that. Let me try one more example. So here we will explain, let me just adjust the parameters. We will explain a versicolor instance for the versicolor class. So here we're explaining this star for the orange class, and we get some sort of an explanation. Now the question is, what the explanation will be for virginica class for the for virginica instance. So this will be located somewhere around here. And again, I'll give you a moment to think about it. And surprisingly, the explanation is the same. And again, there's a good reason for that. Now, a final trick question. What if I move this partition a bit to the right? So I'll split at petal length at 4 centimeters. The explanation will change, which might have been expected. But now, do you think that if I explain the versicolor instance for the versicolor class, which was somewhere around here, would you still get the same explanation? And the answer is no, the explanation is quite different. And this is in how the algorithm is operationalized. So you need to be very aware of how you split your data and how you generate your explanations for them to be meaningful. I have one more example of individual conditional expectation partial dependence, but I'll leave it for you as an exercise. Right, so what are the key points? First of all of these explainers are just diagnostic tools, and they only become explainers when we understand their properties and can interpret their outputs correctly. Also, explainers are not monolithic tools. They need to be parameterized and configured for the application at hand, or alternatively tailor-made with transparency by design. So where to go from here, now that you're curious about why it didn't work as you expected? Well, all of these examples are built on top of our Python toolkit for algorithmic fairness, accountability, and transparency called Fat Forensics. You can read more about it on its website or in this paper. Also, we have organized a hands-on explainability tutorial last year at ECML PKDD with all of the recordings, slides, and computational notebooks available on the website. And these interactive slides will be published on our events website in the coming weeks as well. We have also received a grant from the Alan Turing Institute to create online interactive learning resources about machine learning, interpretability, explainability, and transparency. And this will be published in October this year. Finally, I'm a member of the Taylor Network, and here we're working towards trustworthy AI. So please look out that space for more papers. Right, thank you so much for your attention, and I'm happy to take questions now.
Thank you very much, Kacper. That was absolutely fascinating. Let's jump over to questions. First question's got 12 votes, so I guess a lot of people in the audience are wanting to know the answer. This is from Ricky. They say, sorry, this question isn't about your presentation content, but what software are you using to embed your Jupyter notebooks in your presentation? This is amazing.
All right, so if you can still see my screen, this may break. Oh, you can't. And so I'll just.
No, there we go. We can see it now.
All right, so it's basically a Jupyter notebook, which you should be able to see now. Yes. And there is an extension to a Jupyter notebook called Rise. And with Rise, you can specify what type each slide has, each cell in the notebook has, and then you can make it into interactive slides.
There you go. Beautiful. You've just made 13 people very happy, I think. So there you go. 14 now. Okay, let's go to the next question. Thank you. Thank you very much, Kacper. Okay, this is from Waleed. Could we potentially use occlusion as a data augmentation strategy to increase robustness?
Well, I think so. But then again, the color that you use for the occlusion will affect the result of that. So there is an alternative technique, which is a bit more intuitive for humans, where instead of occluding parts of images with color patches, you cut out some objects from other images and just paste them on top of whatever you want to hide. So for example, you may want to cut out a cat from another image and then paste it on top of your image to hide something. So I think that would be more effective. This is called BAM, I believe, benchmark attribution method. There's a publication from Google Brain about that.
Awesome, thank you. Let's go to the next question. This is from Saravanan. How do you evaluate the quality of your explainability methods in a quantitative way, as well as just qualitatively by inspecting?
Oh, that's a very good question. It's really not, there's no universal way to do that, so it's very difficult, but we did come up with a few ways to do that for tabular data. So you've seen me splitting the features at different points, and there are some metrics that you can use to guide how to split them. So for example, you want to optimize purity of your splits. So you want each segment in the split to have as many points of one class and as few of the others. You also want them to be as densely populated as possible. And to this end, you can use standard machine learning metrics like, for example, gene impurity for classification, or mean squared error for regression or probabilistic predictions. And there's quite a lot of resources about that in our hands-on tutorial from ECML PKDD. So I encourage you to have a look at that, because you can learn more about it there.
Awesome. Lots of good recommendations. Thank you. Next question is from David. It says, basic question. I see 2 eyes and a wet nose, tennis ball secondary. We recognize dogs based on experience. How can an AI system build on experience?
Well, I don't think I can answer that. This is why we try to explain black boxes, I suppose. And this is usually post hoc, we know it we know it when we see it, right? And then once we recognize a dog, we can only rationalize post hoc, say, oh well, because it has eyes and fur or whatever, it's a dog. But the instant you see it, you don't think, oh, okay, how do I analyze this image? I probably should look for 2 ears, a nose, a muzzle, etc. And then how do you classify it as a specific breed of dog? I don't think we can relate it to how humans comprehend images, and this definitely this is definitely outside of the scope of machine learning explainability right now.
Awesome, thank you for that. Let's go to the next question we have here. This is from Colin. He says, thanks for the talk. How scalable do you think this approach is, i.e. for highly complex images in open world contexts, for example?
I don't think it's very useful, to be honest. There are so many variables that come into play. There's so much randomness there. You need to generate your sample in order to create the explanations. You need to choose the color, like I've shown you. There are so many parameters, and depending on how you pick them, you'll get different explanations. And then also splitting images into subregions. There are other methods that allow you to identify general concepts to explain an image. But still, I think we are a long way from true explainability. There are some researchers who argue that this sort of explainability, which is called post hoc, when we have a separate black box predictive model and then an explainer on top of that, are not very useful just because of that reason, because we build more complexity on an already complex system. So we should design systems that are transparent by design. And there is some work into that with decision trees built on top of neural networks, etc. So I think that if we really want true explainability, we should look into methods that are transparent by design.
Awesome. I think we've got time for probably one final question for you. This is from Julio. Is the example on feature partition what basically is done by decision trees?
Yes, and again, that's a very good question. And if you look into our hands-on tutorial resources, we explore that further, and we actually can show that using a decision tree as the model that is used to generate the explanations is way more efficient and intuitive in comparison to what happens in some other surrogates where you build a linear model on top of your feature partitions to do that. So I again encourage you to have a look at our hands-on resources from that tutorial.
Thank you very much, Kacper. And again, unfortunately, we're running out of time for questions, but again, there's still lots coming through. So it looks like, Kacper, you put your email at the end of your presentation, assuming you're okay with people to contact you with any questions direct. And it sounds like all 3 talks, there's been a lot of shared resources and libraries and stuff that people can go check out as well. So thank you so much to all 3, or well, 4 of you, but 3 Research Predicts for coming and sharing your work with our audience today. It's been absolutely fascinating. And thank you so much, everyone, for submitting so many questions and being so engaged. That's absolutely brilliant. And we're going to take a little break now, before we go into the next sessions. They'll be kicking off just after 12 on the 2 stages. So you've got about 10 minutes, almost 15, to go grab yourself another coffee or a tea, or perhaps a wee early lunch, depending on where you are in the world. You can stay here on the Enigma stage. There's going to be an international panel of experts on digital human rights, which will be really fascinating. I'm excited about this panel. Or you can head over to the Turing stage for an academic discussion of whether there will be an AI panacea for healthcare, which also looks really interesting. I'm not entirely sure which one I'm going to be able to watch right now because they both sound brilliant. So as I say, join us back again just after 12 for whichever of those sessions is the one of your choice. And we'll see you very soon. Thank you very much.